Okay, good afternoon, everybody. I'm sorry I'm 5 minutes late. I started the recording of the video of the lecture. So I hope everything is fine with you. It has been a long since we last met, and therefore I think it is useful to make a summary of where we got last time. And let me pass the PowerPoint in presentation mode. So last time we started focusing on just 1 second, because I'm trying to remove this. Perfect. We started focusing on CO2 emissions caused by human activities, and we discussed this graph extensively, where we pointed out once again, because we discussed it also earlier, that energy is responsible for more than 70% of the global CO2 emissions by humans. And let's remember that we are focusing on energy in this lecture. Energy, and we defined energy. We also talked about classification. We talked about primary and secondary energy, and we aim also to discuss renewable energy and other energy sources, because we understood that its energy is fundamental to human development. It's fundamental to sustainable development, actually, and therefore we want to gain a better understanding of what are the solutions for satisfying an increasing demand of energy at the global level. And at the same time, we are facing an increasing need for mitigating climate change, which means reducing CO2 emissions by humans. But as we can see in this graph, more than 70% of our emissions are related to energy production. And then this energy is used in several forms, in industry, in transportation, in buildings, to heat buildings. And this graph gives you a lot of details. And we also pointed out the fact that transport is indeed a significant part, about 1/3 of this 73%, 1/4. And in transport, there is the road transport that is playing a relevant role. So the question here is, as I said, how to cope with increasing energy demand, which are also related to development, global development, in a clean, let's say, clean manner, in order to avoid that we produce this energy by mainly using fossil fuels, as we are doing now. So we also, in fact, discussed this graph where the energy marketed at the global level is shown, classified, depending on the fuel type. And here we see that nuclear is the lowest of these sources that we are considering. Renewables, which do not include nuclear here, it's the second lowest. And then we have natural gas, coal, and liquids. Liquids that are mainly derived by fossil fuels, like oil, and liquids that are derivated by oil. So indeed, what can we see here? What we can see is that in the current situation, and also according to future projections in the short term, because we are talking about a projection of about 30 years horizon, lead time. I mean, in the current situation, and also according to our short-term projections, we mainly use fossil fuels like coal and liquids, also natural gas. But natural gas, as you know, is it's more convenient in terms of CO2 emissions than the coal and the liquids derived by fossil fuels. So we mainly resort to these sources for energy production, and there is a significant and increasing contribution of renewables, which is in a way our hope for the future. And there is an increasing, even if with lighter pace, of nuclear, which is also predicted to keep this slight increase into the future. Let's try to understand some more about these figures. And we also discussed this graph, which shows the global world energy balance. 80%, 81% of the energy production is covered by fossil fuels, as you see, natural gas, oil, and coal. Oil includes the liquids, those that were called liquids in the previous slide. And then we have the renewable. Here, the renewable are placed at a percentage of 14%. Actually, as we will discuss later, this percentage is increased. This graph dates back to 2017. So during these 7 years, the percentage of renewable energy production is increased to about 20%. And nuclear was at 5% 7 years ago. Now it is only slightly larger. And among the renewable, we have the percentages that you see there. Hydroelectricity, hydropower is about 2.5%. Biomass is about 5%. The use of wood for producing energy, for instance, for heating buildings, is at 5%. And then we have very small contributions by solar panel, wind, geothermal energy, others. So indeed, I mean, the figure that is clear from this picture is that, I mean, 80% is still it's still a large majority of the energy production that is related to the fossil fuels. And of course, we are concerned about this, and there are plans at the international level, as you certainly know, to reduce the fossil fuels by increasing the percentage of renewables. And also there is a strong debate about nuclear energy, which we will take the time to discuss, I think, today. Now, another other information. First, let's take into account that half of the global energy is produced by China, the United States, and the Arab state of the Persian Gulf. And the Gulf states and Russia export most of their production. This is a figure that is referred to the situation pre-war in Ukraine. Then you know that the global exchange of energy is changed a little bit after 2022. And these exports by the Gulf state and Russia are largely directed to the European Union and China. And the European Union is not self-sufficient in terms of energy, and China as well. Energy production increases slowly, and except for solar and wind energy, which increase about 20% per year, but we know that their contribution is still limited. But except solar and wind energy, the global energy production is increasing much slower. So our interest here is clearly in renewable energy. It's emerging as an important opportunity to increase global emissions, but in turn, it implies some drawbacks, which I want to discuss with you, because understanding this picture of the global energy budget is extremely important in order to understand what we can do for mitigating climate change and adapting to climate change. So what are the downsides of renewable energy? There is probably the most significant one is the intermittency of solar and wind energy, which is a significant problem because remember that energy, as we already said, cannot be stored. It can be transported, it can be converted, but cannot be stored unless in limited quantities. If you think of the accumulators, the energy accumulators, they have a limited capacity. So if we had to store a huge amount of energy, it's not impossible, but it's extremely demanding. One way to store energy is, for instance, to store water in the domain of hydropower. If you store water upstream, it is an energy storage. On the other hand, we have limited capacity of doing that. So you see the hydropower production covers about 2.5% of energy production, which means that this is a resource, a storage, an opportunity for storage that we can use, but it can cover only a limited amount of the needs. So intermittency of renewable is then a problem. And because, of course, energy demands are not constant in time. And therefore, we need energy when it is needed. We need to provide energy when it is needed. And the intermittency of solar and wind power makes this, of course, a problem. It's a problem because we cannot regulate wind speed, and also in terms of solar energy, of course, we cannot regulate and modulate the incoming energy from sun. So this is the first problem. A second problem is the environmental impact, because both solar panels and wind panels imply significant environmental impact. We will talk about this later, but I want to mention that besides the impact on the landscape, which is relevant, because, I mean, you can perceive if you visit solar farm or wind farms, you can really perceive, and you have some figures in my website, you can really perceive what we are talking about in terms of impact on the landscape, on the visual, on the skyline. There is also an impact in terms for wind farms in terms of noise. They are extremely noisy. And for solar energy, there is an impact related to the loss of land, which cannot be used anymore, for instance, for agricultural purpose. I mean, of course, one may say if we place solar panels on the rooftops, it's not a problem. We are not losing any land, but keep in mind that in order to obtain a very massive production, the production of a lot of energy, we need indeed to cover very extended surface. So usually solar farms, the most important ones, are placed in areas over the landscape, in land areas that are very extended, and therefore there is a loss of land. Of course, we try to place them in arid regions, in regions where the loss of land doesn't imply a loss in food production, but still it is not always possible, because we cannot place solar farms very far away from human settlements. We cannot, if you transport energy in space, you cause a loss of efficiency, and also, you know, long electric lines mean relevant cost. So usually I mean, production of energy is to be located where or close to where the energy is used. And usually the energy is used in the proximity of human settlements, and human settlements are located where there are the conditions for ensuring human life. So usually settlements are not placed in the middle of a desertic area, but they are placed in the vicinity of locations where it's possible to produce food. So the moral of the story is that very often extended solar farms means an impact on food production, and there is also an impact on the water cycle, because the coverage of the land with solar farm implies reduced infiltration of water into the soil, which means that water resources are also impacted. So these are the downsides of renewable production, which of course we need to be aware of and to plan accordingly. And there are still open questions. So when we say that, for instance, for Europe, we want to reach carbon neutrality by 2050, as the current European plans suggest, we still have to find an answer to open questions like, for instance, energy production with renewable energy, or other sources that don't imply CO2 emissions. On the other hand, there are these downsides that we need to carefully consider. So, other interesting statistics. If we look at the global final energy use, we have to take into account, we already mentioned more or less these percentages, more or less because we refer to other databases, but and this is information that comes from the International Energy Agency. It's dated 2017, so it's a different source with respect to the graph that I have shown you of the CO2 emissions. Anyway, we see here that if we look at the global energy use, the residential part is about 1/5. Transportation is a little bit less than 1/3. Industry as well, a little bit less than 1/3. And then we have another 1/5 that is due to other uses. So why these numbers are important? Because in order to cope with the increasing demand of energy, there is a fundamental question regarding energy saving. We are convinced that in the future we will be able to reduce the loss of energy. And reducing the loss of energy by, for instance, avoiding as much as possible energy transformation. Energy, in order to be transported, very often needs to be transformed. And for instance, it can be transported in the form of electricity, but then we have to convert the energy into electrical energy, which means, as we have seen, loss of some energy, which is not really an energy loss, but we lose the capacity of part of that energy to produce work. So it's not an energy loss, but it's anyway a reduction of the work that we can derive from energy, which is in practice a loss from our point of view. And therefore, we need to avoid these losses by reducing the transformations, and we need to focus on energy saving and devise innovative solutions for reducing, or let's say mitigating the energy losses. And so we have to take into account these numbers, because these numbers clearly tell us what are the sectors that are more important. It's quite true that these numbers basically have more or less the same amount. So we cannot say that the residential part of it is negligible. And and therefore we cannot say conversely that transport and industry have a much higher priority. But on the other hand, it clearly shows that what we can reduce in transportation, what we can reduce in the industry, what we can reduce in the residential part has an implication, have a positive impact on our energy demands. Regarding transportation, keep into account that there is an issue that is often not perceived by the public. There is the feeling that in order to reduce the CO2 emissions, the global CO2 emissions, we need to reduce the use of transportation means that directly produce CO2 emissions, like airplanes, cars. So there is a push, for instance, for using electric engines by taking the train, by buying electric cars. But unfortunately, the amount of energy that we need to produce, we need to use for moving, is fairly, anyway, very high. So it's not that by using electric cars we use less energy. Conversely, the efficiency of electric engine is much lower than the efficiency of an internal combustion engine. So the efficiency of electric cars in terms of energy that is used for moving is lower with respect to the efficiency of a traditional car. This means that given that more than 70% of the emissions are related to energy production, this means that even when I take the train or even when I use the car, I cause an emission of CO2 because the electric car uses energy. It uses more energy than a traditional car. Of course, it's an energy that is partly produced with renewables for 20% of it, but 80% is used by burning fossil fuels. This means that if I use an electric car, 80% of it, at least, probably more, because the engine is less efficient, implies anyway CO2 emissions. So if we want to save CO2 emissions, we have to reduce moving, traveling. It's not just enough that we take the train or we use an electric car. It's not just enough that we don't use traditional cars and we don't use planes. Anyway, by the way, you saw that the contribution of planes is very small with respect to the total. If we want to mitigate CO2 emissions related to transportation, the first solution is to reduce travels, to reduce transportation. And then, of course, we gain something if we use electric engines, but it's not the final solution, not now. And this is something that is usually not perceived because indeed, or you may have seen recently on the media that these issues have been discussed, because if one takes into account also the larger quantity of emissions that is needed to produce an electric car with respect to a traditional one, if one takes into account the need for displacing exhausted batteries, it's not really clear if full conversion to electric cars or to electric engines in general will allow to give a significant contribution to carbon neutrality. This highlights a very big question. So related to this target of carbon neutrality. And ideally, I mean, this would be the final solution if energy is produced with clean sources. And but now still 80% of it is produced by using fossil fuels. So it's a very comprehensive set of strategies that we need to set up and apply if we really want to move forward with the objective of, with the target of carbon neutrality. And it's not immediately clear how this will be achieved. There are open questions, as I said. So let's have a look at the global energy consumption from 2000 to 2021. In this graph, each column represents a year. If you count the columns in these graphs, they are 22, okay, from 2000 to 2021. And it's interesting to see from these graphs the pace of the global energy consumption, depending on the fuel. So coal, there has been a significant decrease of the use of coal along the years, and in particular in the past 10 years or so. And this is for sure a positive side of the story. By the way, look at the singularity of 2020, of course, because we had a long lockdown at the global level. Also in 2021, some weeks of lockdown, but not as long as in 2020. So if you look at the singularity of 2020, it's interesting because it allows us to understand what we gained with, a full lockdown that was, it depends on the countries, but in Italy, I think the full lockdown was like 3 months by putting together the spring lockdown and the autumn lockdown. Was about 3 months. And in other countries, in some countries it was 0, and in other countries was I think that probably the Italian one has been one of the longest. It is around 1/4 of the year, but still you see that in terms of energy consumption, even if we put transportation to basically 0, and of course we kept other energy consumption which are not related to transportation. But there was also a decrease in the number of buildings that were heated up because they were closed, public buildings, etc. So you see that indeed there is a decrease in the use of fossil fuels, coal and oil, but not that huge decrease. So when some people say 2020 has been a test year, I don't think so, because if you look at the energy consumption, we consumed a lot of energy. We can see the footprint of 2020 here, but it's not really a very deep footprint. And also, if we look at the use of oil, it's not as decreased as coal. Keep into account that coal is, is a problem from several points of view. It's not only the CO2 emission, it's also air pollution. It's indeed a fuel that we should really try to minimize in its use. So I think that the policy was more efficient for coal with respect to oil, and in fact you see the difference. But still, also in the use of oil, I think there has been a decrease. It's not immediately visible here, but there has been a decrease. Of course, we don't see the same reduction in the use of natural gas, because natural gas was actually used as a compensation for coal. And by the way, in the past 2 years after the war in Ukraine, probably in the Western Europe, there has been an increase of the use of coal at the expense of natural gas. Natural gas is still much used, but the fact that the use of natural gas is increased can be seen as a compensation of the reduced use of coal and oil, or at least a compensation for mitigating the trend. So if you look at the trend of consumption of the natural gas, is more significant than the trend for oil. And the reason is that natural gas has been used as a substitute for oil where possible. Natural gas, however, is not the final solution because it's something that is not really available. It's available only in some places, and you know, to transport it, it's not easy, and it's also related to international cooperation. It's impossible to create a global self-sufficiency for countries in terms of natural gas, of course, because it's available only in a few places, which means that the use of natural gas can be perturbed, impacted by geopolitical drivers, which is not precisely what we want to do, because I mean, what we should target is a stable situation, stable also with respect to the onset of international tensions. Nuclear, I will talk about nuclear later. Of course, let me anticipate that it's a hot topic, because nuclear, it's a very interesting opportunity, indeed interesting. But I will discuss a bit later, because I added a section in my lecture related to climate and energy just today for discussing the use of nuclear power. And then there is hydro. Hydro is increased in time, but really not that much. Not that much. Renewables, they are sharply increasing, and their rate of increase is about plus 16% per year. So as I said, now we are around 20%, which means that we can expect an increase year by year, a rapid increase year by year. Probably it's not enough to reach neutrality by 2050, but it's an interesting opportunity. On the other hand, we have to take into account the downsides that I mentioned before. Overall, I think these graphs are interesting, and we should try to get an updated picture, because you understand that the global situation from 2021 to today, only 3 years passed, but it's completely different. And therefore, this also highlights that there is a significant uncertainty in any prediction that we can make. Okay, so let's move forward, and let's have a look at a graph that partly we already discussed. This is quite old, 15 years ago, and in fact, you see that the rate of renewables is about 16%, so it's lower than the current 20%. I think that you know, we already know that fossil fuels are about 80% of the total, and nuclear, we had in mind a larger percentage earlier, but it is comparable to this. What is interesting in this graph, because the left graph is a pie graph, which shows the partition of the energy use, global energy use, by these 3 sources, fossil, renewable, nuclear, and this doesn't say anything new to us. What is interesting is the graph on the right part, which is a zoom over the renewables and the percentages of each renewable. We already discussed a little bit this repartition. On the other hand, this is much more detailed. And this is energy, remember, not electricity, it's energy. So it's biomass heat, 11%. It's a significant percentage. Actually, you know, some interpretations don't classify biomass as a renewable source because it takes quite a long time to be produced. But let's consider it a renewable. There is solar hot water, 0.17%. Remember that solar panels can be used to produce electricity or to produce hot water. It's the efficiency is different. It's more efficient to produce hot water than producing electricity, as you can understand, and also the duration of the plant is longer. Geothermal heat is very interesting, but only the contribution is very limited and related to only some part of the globe. Hydropower, the percentage is similar to what we have seen before. Before it was stated at 2.5%, here it's 3.3%. Keep in mind that depending on it's not easy to quantify the global energy budget. So depending on the institution and the agency that makes the computation, you can find small differences. So it's not a reason of concern unless provided that, of course, there are not striking differences. In this case, hydropower is classified as a source that may contribute from 2.5 to 3.5%, which is fine in terms of energy. Ethanol is 0.5%, biodiesel 0.17%. You may remember there was significant interest with respect to biodiesel, which is produced by vegetable oil from vegetables. Some years ago, there was an interesting debate on this. Actually, it turns out that we can produce in this way only an quantity. Is a fuel that is, it works. And it is indeed a renewable, but on the other hand, the occupation of land, the land occupation for producing fuel would be probably less convenient, would make it less convenient in terms of land occupation with respect to, for instance, solar farms. And now biomass electricity, 0.28%, wind power, 0.5%, geothermal electricity, 0.07%, solar power, 0.06%, and solar CSP, I think it is related to, I don't remember, I'm sorry for that. I think it is related to probably hot water. No, solar water is up there. But anyway, it is a small percentage of energy that can be derived away from solar activity, and then the ocean power is indeed very small. These are listed in decreasing order. Ocean power, by the way, is it's power that is produced by using the motion of waves, and to use, I think we should check whether, according to the source, ocean power includes only the motion of wave, or it may also include the energy derived from solar farms placed over the ocean, because this is an opportunity, of course. For instance, some of the ocean platforms that were used to extract oil formerly, you may know that in the EU there have been restrictions that have been imposed on oil extraction from the bottom of the seas. And as a result, several of these platforms need to be dismissed. One possible solution is to cover them with solar farms. Of course, there is the problem of energy transportation, but the Mediterranean Sea, the Adriatic Sea, they are not very large. These platforms, in some of the cases, are placed in the vicinity of the coast, and therefore they can be used for this purpose. It's indeed an interesting opportunity. Or in other cases, they are equipped with combinations of, for instance, wind farms plus, because in the middle of the sea there is a lot of wind, of course, plus the wave generator the wave generator that uses the energy of waves to produce electricity or other forms of energy, but still the contribution is still very reduced. So in a way, you understand from here that if you want to increase the percentage of renewable, you need to act over several different fronts. You have to integrate several different solutions. And sometimes it is compelling to try to understand whether the costs are sustainable, because there is a relevant cost associated to renewable energy production, and it is a question whether these costs are sustainable, because these are public resources, and you know the taxation has an impact that is larger for the families with less resources, the people in general that have less resources. So it is indeed a question. And I think that here there is nothing new with respect to what to my previous considerations. And once again, let's take into account the difference between energy and electricity. They are not synonym. We already discussed the difference. Energy may be available in different forms, and one of these forms is electricity. When we look at the figures for electricity, there are differences. For instance, renewable cover, as we mentioned, 20% of the global energy production, about 20%. But if we look at electricity, they cover about 30%. So they are close to 1/3, which is, of course, important, because electricity, much of our needs are related to electricity. And if we look at hydropower, which contributes to the global energy budget for about 3%, as we have seen, 3-4. If we look at electricity, then hydropower becomes more significant, because it produces about 80% of the electricity that we use today. So it's important to be aware of the differences, and energy is also what we need to heat a building, but usually we don't heat a building by using electricity. So we have to be aware of, as I said, of the differences. Even if I mentioned heating buildings, if we want to reduce the consumption of natural gas, it's clear that we need to resort to electricity also to heat buildings up. These evaluations need to be carried out at the global level, because when we talk about reduction of emissions, as I already mentioned, we need to make a model that works at the global level. Its emissions travel, CO2 travels in the atmosphere, and therefore it is something that requires an action at the local level, but the evaluation of the policy is a global one. On the other hand, to make these computations, this assessment at the global level, you understand the difficulty. And there are countries where we are used to monitor everything. There are other countries where this is simply not possible. So if we think at the human emissions of a very large country, which involves then emission sources that can be easily monitored, industries, but others like households or let's say housekeeping, what you need to, the emissions that you need for the everyday life, and they are difficult to quantify. So, as I said, this explains the uncertainty and also explains the complexity of the problem. It is really a complex problem to make an energy budget at the global level. It's already a problem making an energy budget at the scale of an individual house. So think of the global scale. Now, this graph, which is it's updated. It's on the website, but it's still the old version. I don't know why, because I thought I uploaded it also on the website, but in the PowerPoint, you can see the updated version. These are the addition to the renewable energy capacity. And basically, additions means the plus every year. And on the vertical axis, there are gigawatts. And for the past, let's say from 2017, you have the split of the addition in the different components, in the different renewable energy sources. So solar energy is increased, and wind energy is, it's onshore wind energy is increased, but not as much as solar energy. And offshore wind is increased, but still a limited contribution. Hydro is more or less the same. And biomass is more or less the same. So, in any case, keep into account the rate of increase, which is about, you see, from 2019 to 2020, we passed from 200 to 260, so it's more than 20%. And then we had smaller increases later on. And there has been an overall average increase of about 16% per year, as I said. So it is indeed a remarkable increase, but still, this information indicates that we have a long to go to cover our energy demands with only renewables. And you may think that plus 16% per year is a lot. But we have to expect that this rate of increase is not kept constant in the years. As we will expand our capacity, the increasing trend will become not as significant, because of course we are occupying the land with solar farms, wind farms, so we cannot continue occupying lands with the current trend. There will be a point where we need to, in a way, find alternative solutions if we want to cover the energy demand while keeping the current level of development, which of course we want to keep. Now, here it's interesting to look at renewable energy. Sorry, this is not. This is a graph of total energy production by countries, and it is placed here in the context of renewable energy because it is useful in order to understand where action is needed. The graph refers to total energy production, and so here we have two axes, two vertical axes. Okay, we have one horizontal axis, which is time from 1980 to 2015. The graph gives data up 2012. It's not much changed. The progress is not much changed in the past 10 years. And the vertical axis, you have on the left vertical axis, the production, the vertical axis of the red line, which is the global world. So clearly you see a sharp increase of energy production. Look at the red line. Now, on the right, you have the vertical axis of the individual countries. They use two axes in order to make the graphics and the progress comparable. So the colors, yellow is China. China, you see a sharp increase after 2000 of energy production. Brown is Russia. Light blue is Africa. blue is United States, green is Europe, dark green is Central and South America. So you see what are the most important producers: China, United States. Europe doesn't produce a lot of energy, and also it is quite stable energy production in Europe, because part of the needs of Europe have been covered by Russia. So here you see the significant role of United States, China. Here it's not depicted the progress of the Arabic countries. So you see that indeed this allows to understand the key roles that have to be taken, the key actions that have to be taken at the international level. Now, let's focus on electricity and renewable electricity. This is not total electricity. It's a focus on renewable. Okay, this explains the difference between the percentage for hydro that you can see here and the percentage that I gave before. Before I said 16% of electricity is generated by hydro, which is fine. If you focus only on the renewable electricity, hydro produces 45% of the renewable. And then we have nuclear, it's 28%. Here, nuclear is taken as a renewable, classified as a renewable. Actually, nuclear doesn't produce CO2 emissions, so it can be put in the same category as hydroelectricity if we focus on CO2 emissions. They are at the same level, no emissions, or let's say almost no emission. Of course, if you think of building a dam or building a nuclear power plant, then there are emissions involved. But for the production of energy, it's clear that they can be classified at the same level. If we talk about the character of being renewable, actually nuclear cannot be said to be renewable because the uranium is not renewable. And the uranium is basically for nuclear energy now, it's the only fuel that we can use for producing electricity in large quantities. Anyway, nuclear is 28, it's significant. If we consider nuclear as a renewable, it's a significant percentage. It's comparable to hydroelectricity, it's a bit lower, but not much lower. And keep into account that nuclear, the progress of nuclear energy production has been slowed down recently. Wind is 13%. Solar energy is 6%, biofuels is 5%, other is 3%. Now, hydropower plays a significant role, not only for its large percentages, about half of the renewable electricity. Hydropower is also important because it allows storing energy, and I try to better explain. When you have a production of renewable energy by wind farms, solar panels that needs to be stored, a possible solution is to pump hydropower, to pump water uphill, upstream. Indeed, there are several hydroelectric plants that can be used to generate hydropower or can receive power and pump water back upstream. You may have heard of the disaster of the hydropower plant in Subiana. And you may have heard that it is a plant that can work in two directions. it can receive water from an upper lake to the Lake of Subian, which is placed at a lower altitude. It's downstream. And then in making this jump, water can generate hydroelectricity, but these turbines can also work the other way around, can receive electricity and pump water back from the Lake of Subiana to the upper lake. So hydroelectricity this is a common solution. This is a solution that is very usual. Hydroelectricity is indeed a resource, hydropower in general, also for storing energy. So to answer to the question, to the challenging question, how can we store, how we can modulate the production of energy from renewable sources, which are intermittent, the answer may be using hydropower, which is a solution for storing energy. And this highlights the essential role of hydropower. Why hydropower is important in the context of climate change, in the context of climate change mitigation and energy saving. Now, let's focus on wind energy generation. So we are focusing on renewable. We talked about hydropower. Wind energy is, I go back one slide, is covering about 13% of the renewable energy production. So here is a graph showing the progress of wind energy generation by region. And you have here the contribution of Asia, Europe, North America, and then which are the main producers, and then Africa, Middle East, and South and Central America. So basically, you see that there has been a large increase in Asia, an increase in Europe, not as large, and an increase in North America. And this brings the graph to the current level, which is a very significant level of production of wind energy production. This is measured in terawatt hours per year, and the figure includes both onshore and offshore wind sources. This is taken from our working data, and you can get the update here because it stops 2020. But if you look at, of course, nothing changes. But if you're interested in an updated picture, you can look at our working data. Now, next is the wind power potential. This is a map of potential wind resources. And this is a map of basically of wind velocity and duration of wind velocity. And you can see what are the countries, and red means high power, our high potential power, while blue means lower power and green means average value. You can see a map of the zones of the globe which can be suited for wind power generation. That is to say that this is just potential. You have to take into account first that transportation of energy implies a reduction of efficiency, and which is not taken into account here. And in some cases, it may not be possible. So the potential is not actual production. And this is the first thing that we need to take into account. Second thing is that these maps are based on statistics of wind velocity. So it shouldn't be a surprise that some regions that are scarcely populated, also for the very reason that environmental conditions are not easy. Like look at the very south of America, Patagonia, and Greenland. So these regions are scarcely populated while offering a huge potential in terms of energy. And indeed, here you have clear that potential energy is different from actual energy. On the other hand, once that we found an efficient solutions for moving energy, it's clear that this map highlights a region of the world that could be more favorable to human settlement in the future, because in the future there might be some features, environmental features, that today are not important and in the future may become important. So today, basically, human settlements are located where there is water, are located where there is the opportunity for producing food, and where the living conditions are favorable. In the future, the energy potential may become a favorable condition to human settlements, which means that in the future, the potential energy availability of some regions would be an incentive for certain chains of production to move there. This is an interesting perspective. We, on the other hand, we already had some demonstration of something similar that happened in China. There was a period where producing, locating the industrial production in China was very convenient, and it's still, to some extent, up to the pandemic, was very convenient, and still, to some extent, is convenient. And therefore, there was a kind of industrial migration from the Western world to Asia because of the more favorable conditions for certain types of production, which made Asia more attractive, like it was in the past for the production of certain goods. So indeed, and this is also happened in history. As I said, La Via della Seta, the route of the, sorry, I am missing the word of Seta in English, but the route followed by the ancient trades, you know, were driven and were originated by industrial development or commercial development, not industrial, commercial development, which it is something similar to what may happen now with the market, with the energy market. So indeed, this potential may for producing energy with renewable in a world where the fossil fuels will become less and less available, may originate some future developments which may open new perspectives. And I tend to see these opportunities as these developments as an opportunity. Of course, we have to do that. Any development should be seen, should be assessed, analyzed by looking at the positive sides, which are always there in any development. So I'm trying to look at the opportunities that this may trigger. Now, solar resources. This is a global irradiation map. And in order to highlight what are the countries where there is the highest potential for the production of solar energy. Same reasoning as before. I mean, this is highlighting a possible future for these countries. And you see that in terms of solar power, the countries that are more equipped are those that today are part of the low GDP world, so low gross domestic products world. And this may open interesting opportunities for the development of these regions. And of course, there are also concerns related to this, because if some countries are, in a way, are in a critical situation from the point of view of economic resources, and suddenly they become richer in some resources, there is the risk that there is an appropriation by the countries with more resources of the emerging resources. This is already happening in Africa with the phenomena that is called land grabbing, which means that in a certain part of Africa, where there is a lot of potential for food production, there are some countries that are buying lands. They are buying lands which are cheap in order to produce abroad the food that they cannot produce at the internal level. Land grabbing is a phenomenon that is widely studied, starting from about 10 years ago, and you can find a lot of information if you look over Google about land grabbing. And there might be the concern that also in terms of energy, we may have a phenomenon called like energy grabbing. Of course, still it's not easy because, as I said, one thing is to transport food, another thing is to transport energy. It's not so easy. But on the other hand, this is something that should be, in a way, governed at the international level. It's not easy because we don't have a global government, and we probably don't want a global government because also the sovereignty of each country is important. But on the other hand, we need a global consultation, and we know more than ever during these years how this may be difficult. It can be indeed very difficult to rely on global consultation. Now, this is a map of the climate change performance index. And what is the climate change performance index? If we talk about climate policies, which of course are related to energy production and are also related to other aspects, other human activities that produce the CO2 emissions, it is interesting to look at what are the countries that are performing better in terms of reducing this energy or reducing these emissions of CO2. The Climate Change Performance Index, which is identified with the acronym CCPI, is a scoring system designed by the German Environmental and Development Organization. It's called the German WatchED, to promote transparency in international climate politics. And I decided to show this map because I think it is interesting indeed. Here, in the green countries are those performing better, and there are some results that I think will, in a way, astonish you, will amaze you in some way. And in the yellow, we have medium performances and low performances in orange and very low in dark red. And I think it is, as I said, it's interesting. Let me see if we can find an updated diagram. I'm not sure, but let's see. Let's open another. another internet window. And let's look for CCPI. Maybe that we can find it straight. CCPI. Climate Change Performance Index, here it is. And let's see. This is related, there should be a figure here related to 2024, which is more recent with respect to the one. Okay, there is no big differences, but and Ukraine was not rated, but you see that there are more categories. So here Italy is no more placed in the medium range, but in the low range. And there are also two scales of green, but the very high is not large. I don't see any occurrence of it actually. And then we have also the low rating that is indicated in gray. So this is an interesting, it's an interesting map, and this is why I decided to show it here. And as I said, it's related, it's strictly related to energy production. Now, let's look at the solar farms and some more discussion on the environmental impact of solar farms. And I added a section on my website. I already anticipated the content. Here you can perceive the visual impact. And it is something that is really important. This is not placed, I think it is placed, I think in Italy actually. And you understand, it's quite a huge stuff. And you can also understand the difference in terms of greening. This area that are covered by solar farms are not green. And you can also understand the impact on the water cycle. We are talking about an extended part of land where rainfall doesn't fall anymore directly on the soil. It falls over the mirror, over the panel, and then from the panel is delivered to the soil, but in concentrated rills. So it's clear that infiltration is reduced, and therefore ecosystems suffer from it, and also the risk of flooding. Probably this is an effect that is similar to deforestation. There is no water that is intercepted by vegetation. And there are several papers on the hydrological impact of these farms, which is, it's relevant. This is another interesting addition that I wanted to make on my website on the cost of solar farms. And this is, let me refer to the website directly because there is some more information. 1 second. Here we are. Okay, you see that now there is there are these two figures included from yesterday, I think. This progress, it's declining prices for photovoltaic panels. This is photovoltaic panels, they convert sunlight into electricity. This is interesting because, as I said, these plants for producing renewable energy entail a significant cost, imply a significant cost, which is a public cost. And therefore, there are a lot of concerns related to this because it means that taxation has to be increased to support climate change mitigation, to support decarbonization, to support energy carbon neutrality. It's interesting to observe that indeed the price of photovoltaic panels is decreasing a long time, and the reason is that it is decreasing as long as we have an increasing installed capacity. And indeed, there has been a study that proposed a law stating that solar module prices have dropped about 20% for each doubling of installed capacity. So it's a kind of learning rate, and this law, so 20% drop for each doubling of installed capacity, is called the Swanson law. And it is interesting because the Swanson law, in a way, tells us that in terms of cost, we may expect a significant decrease, even if you understand that doubling the capacity is easy when you are at the beginning, when you start. But we are already in a situation where the installed capacity is much large and doubling it is not easy. But it is interesting, and you see here basically also the timing. 1980, the price, 1990, 2000, 2010, and 2020. And you see that from 2010 to 2020, we passed from about $2 per watt in terms of price for these panels, and now we are at 1/5 of dollar per watt in only 10 years, 10 years only. So it means that indeed, as we expand this, it becomes more sustainable in terms of cost. And then, of course, there is the discourse of impact, of environmental impact. But in terms of cost, we are becoming more sustainable. Okay, perfect. Now, I want to start now a digression on nuclear energy because I think it deserves a separate treatment. My proposal, given that I also need to open another PowerPoint, I would propose to make the break now. Do you have any question? Okay, we have also a few remotely connected students. So I take this opportunity to give an announcement. Next Monday, we have the last lecture. And during next Monday, I will open the survey for getting students' opinion. It is extremely important. I will send an email to you, and I will also send an email and a message over the Teams chat. I don't think anybody's reading it, but I want to make this very clear. It's extremely important that you submit your survey, no matter if you attended a few lectures only or you never attended. Because in any case, you can give your evaluation of my teaching in terms of educational material, educational documents, etc. And it is extremely important because for some reason, as you may have noticed this year, even if the course was full, so 200 students have booked, the attendance was not as large. So probably the reason is that last year it was compulsory to attend the course, and this year, fortunately, I would say it's not compulsory. But it is extremely important, if you're interested in taking this exam, that you submit the questionnaire. It's anonymous, but still it would generate some hiccups if, let's say, 10 students submit the questionnaire and 200 takes the exam. So do your part, please, because of course, it's not possible to monitor who submitted, but it's possible to monitor the number. And therefore, if a few students only fill the survey, it may mean that there was a very not a lot of interest in the subject, in the matter, and the only interested maybe to take an exam on this topic, but we should justify that there is a real interest by students. The survey can be compiled online, so you don't need to be attending the lecture in physical presence. And I will leave it open for 1 day, but please be aware of that. And next Monday, I will also provide online and directly face-to-face to who is attending here, an explanation of the meaning of the questionnaire, how the data will be used, and so that you also get an information from my perspective of what is the purpose of filling the questionnaire, which I think it is highly valuable. Okay, as I said, I will send you an email through Virtuale to remind you of this deadline. And also keep into account that if it was possible for you, I would like to get a last opportunity to see you face to face to give some information on the exam, which I think it's best delivered if we can speak face to face. So if you can make an effort next Monday to attend in physical presence, I will also send an email reminding you that I will give you last information on the exam, which I'm not sure I can make available on time on the website. Thank you very much, and let's take 15 minutes break, and I see you again at 4:28 or so. And yeah, thanks. I'm stopping video and audio now. Okay, here we are. Let me just open the PowerPoint. It's a new one that I made available on the website. It's here. Okay. So let me refer to the website as well. So nuclear energy. Nuclear energy, as we all know, it's the subject of a very interesting public debate. It's very interesting because nuclear energy is indeed producing a significant part of our energy consumption at the global level. It is indeed very promising for the future, also in terms of reduction of CO2 emissions for energy production. Remember, CO2 emissions are covered by human emissions 70%, more than 70% by energy production. And nuclear energy is emission-free, it's clean. On the other hand, you know, what is the subject of the debate is mainly related to the risks, the associated risks, because nuclear energy is hardly considered a clean energy for the fact that there are radioactive scores that are produced and which in any case need to be displaced. And the displacement of radioactive residuals is indeed a relevant matter. And there is also the risk of accident, of something going wrong in the end, the possible release of radioactivity. It's interesting to look at the history of the development of the nuclear solution. So first of all, nuclear energy, I mean, it was discovered in 1938, the nuclear fission. What is the nuclear fission? It's the rupture of an atom, and the most commonly used is uranium. A rupture which is obtained by bombarding the atom with properly selected ions, and then the atom is split into protons and neutrons, and there is a lot of energy in terms of heat that is released after the rupture of the atom. So this was discovered, that this, what is called the nuclear fission, was discovered, as I said, in 1938. And in 1943, I'm checking the date, and in 1942, with an experiment led by Enrico Fermi, the first human-made nuclear reactor was created. And later on, first of all, it was the discovery of this way of obtaining energy was driven by the need of obtaining a weapon, the nuclear weapon, during the Second World War. And it was indeed decisive. It was the decisive weapon that allowed to change completely the outcome from the Second World War. So it was a discovery that was driven by a war. This happens frequently. Usually wars give the incentive for a sharp development in technology. For instance, the First World War gave the incentive to the development of aviation and the use cables for lifting materials, for the technology that is related to the transportation of goods and also very heavy weapons over the mountains by using cables, cable lifts, etc. So the First World War gave a significant impulse incentive in aviation and the technology of bringing, transporting material over the mountains, even the most imperious one. And in fact, for instance, the ski resort were born after, in the 1920s in Italy, after the World War, because we learned how to keep the mountains for allowing the settlement of people, and in the case of the ski resort, to use them for commercial purposes. The Second World War gave an impulse also, again, in the aviation, but also motivated, incentivized the discovery of the nuclear energy. After the war, there has been a significant development of activities finalized the use of this energy for producing electricity. And this is done again through nuclear reactors. How does a nuclear reactor work? So, first of all, let me, from this slide, draw your attention on the last sentence, which is taken from Wikipedia. As of end of 2023, the International Atomic Energy Agency reported that there were 410 nuclear power reactors in operation in 32 countries around the world, and 57 nuclear power reactors are under construction. So how does a reactor work? Let me show first this slide, which is animated and gives a simplified view. So there is a nuclear reactor, which is contained into a reactor vessel, which is contained into a building that is protected. There are several levels of protections. Inside the nuclear reactors, it's placed the fuel, and the fuel is mostly uranium, and it is also feasible fuel in terms of availability of uranium, and also the kind of nuclear reaction that the uranium can originate. And there are some control rods that are placed within each uranium bar, and the control rods are kind of controllers of the intensity of this nuclear reaction, because it is a self-exciting process. Once that the nuclear reaction is started, the energy that is created by the rupture of each atom then triggers a self-perpetuating rupture of other atoms. So we need to be able to control with very reliable systems the proliferation of these ruptures of atoms. And this is done through control rods, which in a way tend to inhibit this self-perpetuation, and they also allow to shut off the reactor in case something happens. Keep in mind that the shut off, it's not an immediate process, it takes some time. Basically, inside the reactor, there is a fluid which collects the heat, and through a pump is continuously circulated between the reactor and a steam generator. So the fluid that is heated up by the nuclear fission is brought inside a water container, a water tank, which and it provokes the evaporation of the water in the water tank. So it is essentially a steam generator. Because keep in mind that a nuclear plant is completely equivalent with to a thermoelectric plant. So electricity is generated in generated by producing steam, and the steam the steam basically induces the rotation of a turbine. And the only difference between a classical thermoelectric plant and the nuclear plant is that in a classical thermoelectric plant, the heat is obtained by burning fossil fuels, typically coal, while in a nuclear plant, the heat is obtained by nuclear fission. So the principle is the same then, generation of steam. The steam actuates, induces the rotation of a turbine, and then an electric generator. And then the steam is brought into a condenser where, through circulation of cold water, the steam is the part of the steam that is not condensed in the process is condensed and used to feed again the cycle of water through a pump inside the steam generator. So this is basically the functioning, and as you can see, in principle it is simple. Of course, here the difference is also the element at risk, because controlling the nuclear reaction is the key and is the critical issue here. And this is also the motivation of some of the reservations, the awareness that the nuclear reaction can go out of control, and the awareness that if it goes out of control, it means spreading radioactivity in the environment, with the possibility that this radioactivity is diffused over a large area, and where with large, I mean area of the size of a continent, is part of the reason of concern. And there is to say that, I mean, it's true that it's not so easy to control a nuclear reaction, but it's also true that also any form of energy production entails risks. And we will discuss of this later. Before we discuss of the risks, let me show you a scheme that is more detailed. Here, you see that there is a detailed explanation of the elements of the nuclear reactor. So there is the core with the rods. You see in gray the rods here. And the bars of uranium in red. So the rods go inside the core, and they have the power of avoiding the proliferation of the nuclear reaction, of course. And then there is here the fluid. The heat part of the fluid is the heated part of the fluid is displayed in red, while the cool part of the fluid is in blue. And here it is assumed that the fluid that is bringing the heat out of the core is water, is directly water. This is a possibility, although the modern reactors usually use a different type of fluid, in order to avoid that there is inside the core a combination of liquid water and vapor and steam, which makes the plant less secure with respect to using a different type of fluid that remains always in the fluid state. So you see that then the heated fluid, in this case already steam, goes out from the core and then actionates what may be a sequence of turbines. And we may have the split in two sequences of turbines, a high pressure turbine and a low pressure turbine. What is the reason for splitting? The reason for splitting is to maximize efficiency, because if you have a turbine working at high pressure, the steam that goes out from the turbine is still a steam under pressure. It still keeps some pressure, because to actionate a high pressure turbine, you need a high pressure steam, and as a side consequence, we have a release of residual steam that is still under pressure. And therefore, it can be used to feed a second turbine, which is a low pressure turbine, which is conceived for working at low pressure, which means that it wouldn't be as efficient if it worked at high pressure. But being conceived for working at low pressure can be used to, in a way, to recycle the residual from the first turbine. And then there is the condensation of water through the condenser, and then the condensed water goes back to, in this case, to the reactor. And then there is the electric generator, which completes the scheme. So in principle, it is simple, and it is very similar to the thermoelectric plant. And this is why, after the discovery of nuclear fission, it was relatively easy to conceive, to conceptualize and make it a reality, the development of nuclear power plants, which this development started around 1950, soon after the Second World War, because, as I said, it was a simple development, and it started in the countries that were richer in uranium, and it also started in the countries that had an opportunity to displace the radioactive scores, the radioactive residuals, and it was also started in the countries that had a lot of space available. Why? Because there was the feeling and the fear that there might be a release of radioactivity, and therefore it seemed to be more appropriate allocating these plants in areas, in desertic areas, in areas that were not in the close vicinity of human settlements. And but still, even in Italy, there was some nuclear power plants were installed, and then in the 70s and the beginning of and in the 80s, there were two accidents which had a worldwide relevance, and the two accidents are in 1979. I'm reading from what I reported in my website. In 1979, it was in the United States, the 3 Mile Island reactor in the United States, and then in 1986, Chernobyl, which is very famous because it provoked a spread of radioactivity over the whole of Europe. Now, these two accidents clearly show that the concerns related to the risks associated to nuclear plants are real, and therefore, there was a slowdown in the implementation of new plants after, in particular, after Chernobyl. Actually, the slowdown was happened only in the United States and in Europe, because in Asia, actually, they kept the pace of installing nuclear plants. Now, there is also to say that at a certain point, after these two accidents occurred, there were concerns also that arose from an environmental perspective. The 80s were in Europe and also in the United States the years of the birth and growth of the Green parties and the Green ideology, which was, of course, motivated by the raising awareness that our development may be not sustainable. If you look at the histories of the concerns related to sustainable development, which was defined only in 1989, the concept of sustainable development was proposed only in 1989, but actually the concerns initiated after the economic boom of the 60s, of the 1960s. And therefore, in the 70s and the 80s, these concerns were growing up and were getting more and more attention, and motivated the creation of the green ideology and the green politics. At that time, the nuclear energy was seen as a serious environmental risk. It was seen as a manipulation of a natural process. And therefore, this interpretation of nuclear energy as a technological manipulation of the natural environment, of course, motivated the ideological concerns that culminated in several, in Italy, in the referendum, which imposed the shut off all nuclear plants in Italy. And the same happened in other countries where there was a public opposition against nuclear energy. At that time, the opposition was, I think, motivated, and motivated by the fact that two accidents indeed occurred. However, in an insight, and I go back to the PowerPoint, if we look, okay, this is an example of a nuclear plant, and you see that also the appearance is not reassuring. It looks like a lot of smoke is spread in the atmosphere. Actually, it's steam. It's the same emission that we get from a thermoelectric plant. Steam, it's water vapor. And it's not radioactive smoke, but at that time it was not fully clear, and also the perception that the people got is that nuclear plants were dangerous and were contaminating the environment, which actually it's not the case, because if nothing happens, the release is not CO2, it's just water vapor. And of course, there is the concern of the displacement of the residuals, and these are radioactive residuals. This is indeed a concern. And let me also say, before I move to the next slide, there were also concerns related to the cost and durability of the uranium resources. However, actually, yes, there is a problem of durability of the fuel, of the uranium resources, but the expected duration of uranium as a fuel is much longer than the expected duration of fossil fuels. So it's indeed we are also going to deplete our reserves of uraniums, but in a very long time frame. And there is also the possibility that with the technological development, we can use other forms of nuclear reaction different from fission, and we will talk about fusion in a moment, and different fuels. However, let's look at this graph, and it's called, it's taken, I think, from, again, from our working data, I could say. No, it's Lancet, sorry, and energy statistics from the International Environmental Agency. It's the hypothetical number of deaths from energy production. Hypothetical because this is not based on a real survey. Okay? It is based on a risk assessment to energy, any form, these forms of energy production, because there is a risk associated with any form of energy production. Of course, if you use biomass, if you use gas, there might be explosions, and if you use hydropower, the dam may collapse, and several accidents occurred actually, more than those that occurred in terms of nuclear accidents. It's not comparable, the number of dams with the number of nuclear plants, because only in Italy we have some, I think, 600 of dams, while you have seen that the number of nuclear plants at the global level is something like less than 500. But still, I mean, there is a risk associated to collapse of dams. If you only look at Italy, we had two major collapses in our history, and several cases in which we had some accidents which were not fatal in terms of consequences, but quite relevant. And if you look at the last accident that we had in the power plant of Subiana, it's another example. So according to these statistics, you see that the mortality from nuclear power plants is much lower than all the others, much, much lower. And at the first place, we have brown coal, and then coal, in terms of hypothetical number of deaths, oil, biomass, and then natural gas. So you see that indeed, currently, and this graph dates back to 10 years ago, 2014, currently there is not a huge risk associated with the production of nuclear energy. Now, what about the future? So far we talked about fission, and let me go back to my website. So far we talked about fission. And in particular, nuclear fission. What is nuclear fission? As I anticipated, but I want to give more detail. It's a particular disintegration process of the atom, during which heavy nuclei, like those of uranium or thorium, is bombarded with neutrons and then split into neutrons that are both positively charged and into two fragments of neutrons. And basically, these neutrons violently repel each other and move away with high energy kinetics. And therefore, this triggers the so-called nuclear reaction, because the atom, once is bombarded with these neutrons, splits in turn into protons and neutrons. And so in this way, as I said, a large amount of heat is produced. Perfect. There is another type of nuclear reaction, which is called nuclear fusion, which may represent an opportunity. Nuclear fusion is the nuclear reaction that occurs in the sun and other stars, with, of course, the production of an enormous quantity of energy. How is it obtained? Two nuclei of light elements, such as deuterium and tritium, at very high temperature and pressure, fuse to form a nuclei of an heavier element, such as helium, with the emission of a large quantity of energy. So there are two nuclei of light elements that fuse together, forming an heavier element with emission of a large quantities of energy. But we need to ensure specific condition for this to happen. And first, the two nuclei can only fuse if they are very close, and the speed at which they collide, they are pushed one against the other, must be very high. So it means that their kinetic energy, and therefore the temperature, must be very high. So how much high the temperature? To obtain fusion in the lab, it's necessary to bring together a mixture of deuterium and tritium to a temperature of about 100 million degrees. So you understand, it's not easy. For sufficiently long times. And then, basically, at this very high temperature, the atoms tend to split and to form a plasma of the heavier element, which is the main constituent of stars and the sun. Now, the temperature of sun is about 14 million degrees, the internal temperature. And, in the sun, there is a lot of space. So, I mean, it's not the small size of a lab, of course. And therefore, the fusion can be obtained to a lower temperature. To create the fusion in the lab, we need to confine the plasma in a limited space, but we need a very high temperature. So you understand what is the problem here is at so high temperature, how can we confine the plasma? So there are no containers in nature that can resist in these conditions. And therefore we have to force a kind of magnetic confinement. We don't go into the detail, but it is essential a very high pressure to make sure that the plasma is contained into a vacuum chamber. Now, this is technically still very complicated, and it means that we are not yet ready to produce at the industrial scale energy through fusion. The advantage would be that there is no radioactivity that is induced. And therefore, it may be a cleaner way of producing energy through fusion. There are also researches that aim to look at what could be the conditions for ensuring a cold fusion, which may be, I mean, the future, but still we cannot do that. Now, the European roadmap towards fusion electricity, as you can read here, envisages the construction of the first reactor that feeds electricity into the grid in the second half of the century. So there is the prediction that by 30 years or so from now, we could be able to generate electricity, nuclear electricity through fusion. So what is the moral of the whole story? Okay, we discussed the issue of the energy demand and the energy production, which is a relevant issue, which is strictly related to climate change and to mitigation of climate change, because it's strictly related to CO2 emissions. And we analyzed the current situation, 80% of energy production is satisfied by fossil fuels. And we discussed renewables as a viable solution to reach carbon neutrality, to avoid that we produce energy through CO2 emissions. The big question is it possible? Is it possible to become carbon neutral, to use only renewable energy in the time scale that we are considering, so by 2050? Or do we need to, in a way, also to accept the compromise of resorting to nuclear energy? Because nuclear energy is certainly a possible solution. Nuclear energy coupled with solar and wind farms, and which are the main sources of renewable energy, would be indeed the key to reaching carbon neutrality in a sustainable way, sustainable in terms of environmental impact and in terms of social costs. But of course, there is the question mark of the public acceptance of the nuclear energy solution, which is probably still not as dangerous as the other forms of energy production that we are using now. But on the other hand, it's clear that there is also an ideological implication due to the fact that this looks like something that is difficult to control. In the current state of our knowledge, we have to either use a nuclear reactor dealing with radioactive material, or use a nuclear reactor which is brought at a temperature which is something that makes, anyway, induces some reservation, because we are talking about, you understand, 100 millions of degrees. And so it is an opportunity, but on the other hand, there are some public reservations. And so the big question is whether nuclear is needed. And the second thing, if we accept the idea that nuclear is possible and nuclear is a solution, there is also this perspective that within 30, 40 years from now, we could obtain nuclear energy in a cheaper way and less risky way. And therefore, the big question is, should we use our resources to force a decarbonization as fast as possible, or would it be more appropriate to make a smoother transition? And so waiting for a time when probably transition will become much more affordable, much more sustainable, much more effective, and much more accessible to everybody. These are the big concerns that have political implication, economic implication, societal implications at large, which are still open question marks. And when discussing about climate change mitigation, we have to keep this into consideration. There are still open marks on technical open question marks, I wanted to say. There are still technical open question marks which are very relevant, which needed to be considered in view of the associated uncertainty. There is not a unique solution, there is not a certain solution. And discussing about these problems and possible solution requires a global approach and requires an approach that is free from ideology. There shouldn't be space for ideology here, but there should be space for an objective and transparent evaluation of pros and cons. because it may be certainly advisable for all of us, in view of the target of decarbonization that all of us think is important, it may be more advisable to conceive a smoother transition rather than an hurried transition that may bring us to make mistakes. And we don't need mistakes when deciding about the future of the planet, about the sustainability of human development. So I'm not suggesting any solution. I'm just highlighting what are the scientific uncertainties and question marks that are still open, and highlighting that, besides the political and socioeconomic arguments, we should also look at the scientific basis and the technical suitability of each alternative that we have. Okay, that's it. I think, any question? Okay, now, I think I was not sharing this. Oh, no, I was sharing the screen, sorry. Yeah, okay, I think we can stop here. And